2019 is an exciting year for many reasons, not the least of which being that it's the 150th anniversary of the periodic table. Back in 1869, that old chestnut of a year, Russian chemist Dmitry Ivanovich Mendeleev decided he needed a little more organization in his scientific life. No more pen and paper lists, no higgledy-piggledy piles of stuff. The fundamental elements of life needed to be put in order in a way that makes sense, gosh darn it. We've put together another video that's an introductory primer on the periodic table, how it works, what information it tells us, and why it's such a nice, neat way of organizing the world's elements over here. And spoiler alert, there are some discussions of possible redesigns. But the focus of this video is something so insane it doesn't even sound real. Elements are substances that cannot be broken down any further. Each is its own type of atom, with different numbers of neutrons, protons, and electrons. They cannot get simpler. They're what we call the primary constituents of matter. If you try and break them apart, you just get those subatomic particles, like the protons and neutrons of the nucleus. And here at the lab, we make new elements. We make new stuff. But how?
So creating an element is really just taking two other elements and merging them together, fusing them into one so we can add up all their protons, because it's the proton number that determines what element we've made. So for instance, we start with something that has 20 protons, which would be calcium, and then we can take another material which has 96 protons, which is curium, and if we can fuse those together, we actually get an atom of element 116. Well, the nuclei have a lot of positive charge, so they don't want to merge naturally. So we have to overcome that repulsive force. Very similar to two magnets that would have the plus sides aiming, they want to break apart. Same thing with the two nuclei. So we use what's called a cyclotron, and it's a particle accelerator where we take that calcium beam and we accelerate it through two large magnets that are shaped both like Ds. And we can alternate voltage across there, and that makes the calcium go faster and faster in a circular orbit until we finally get it to close to the speed of light. At that point, the calcium can be extracted from the cyclotron, and we actually just blast it into our target of curium, and the energy of that accelerated calcium helps overcome that repulsion. And they can actually fuse together and become a new element, element 116 or livermorium.
That's right, element 116 is named after the lab, Livermorium. And all of this is super duper cool, but like, why? Why do we do it? What does making new elements tell us about the way the world works that we didn't know before?
The new elements really help us understand the physics of how the nucleus comes together. As we get out to these higher numbers, things that don't exist in nature, it's really pushing the boundaries of these physics models, and it's really helping us understand really the fundamental physics of how matter comes together. These things are likely made in a very explosive environment like the Big Bang or potentially even a supernova. So these things are existing, we just don't know about it because they're so short-lived. So all of this kind of data feeds into our overall understanding of the formation of the universe and of matter in the universe and how things come together.
Understanding how the universe came together does sound pretty exciting, but making an element is also a long process. Many, many months of beam time go into creating huge data sets that then need to be analyzed, not only by our team, but also our collaborators all over the world. And if everybody sees the same decay chains or a specific series of radioactive decay products that result as an element changes, then all the scientists start to think that maybe there's something there. I mean, if you're gonna announce a new element, you gotta make sure you're right.
That's where our detector comes in. The detector is made of silicon strips, they're semiconductors. The new element comes in and it implants itself into one of these silicon strips. And all of these things are radioactive, which means that they're undergoing decay and they're emitting particles. So that energy of that particle is embedded in the silicon detector, and we can then electronically see what energy the particle had and also what time it was emitted. Then we use a computer to sort through all that data, and what we're looking for are a series of decay particles that have the right energy they're correlated in time and in the same spot in that detector array. And when we see that, we know that those are all part of the same element, and that's how we verify that we made a new element.
So we collaborate internationally for a lot of these projects. It's a pretty world-changing thing, discovering a new element, so it's only fitting that those who work on it are from all over said world. In particular, we collaborate with scientific teams in Russia and Germany on elemental exploration.
The group in Russia is really the one that has made these experiments possible. Their accelerator, the U-400 cyclotron, is very well characterized. It's a blowtorch for these calcium beams, meaning the intensity is just incredible. So without their expertise and their instrument, I'm not sure we would be talking about this today, at least not from a Livermore point of view.
Specifically at Livermore, we're now working on building chemical platforms that would help us understand more about the way that elements like 112 and 114 behave. Some very clever aqueous chemistry coming out of our Forensic Science Center is working to create molecules that would hold these unstable elements in place a little bit longer. See, elements this volatile, like the ones we create, disappear almost instantly. Many of them only last on the order of milliseconds. So to get a longer look at them, we're hoping to build a system where we sweep the element across these molecules we're building to see if it's binding inside the molecules, how it's binding compared to its neighbors on the periodic table, and hopefully learning a little more about its properties. It's kind of like these high atomic number elements are really rare wild animals that we know relatively little about, and the molecules we're working on creating would act a little bit like a cage, so we could trap the element and run some tests. But what's next in the big picture? I mean, does the periodic table keep expanding? What does the future of the periodic table look like?
There's the physics answer, which is how far can you push a nucleus and how heavy can you make it and still define it as a nucleus. And I've seen different answers for that. I've seen people say in the low 130s might be the limit for that. But then there's the actual physicality of doing that experiment. How do we detect something with now a sub-millisecond half-life? How do we transport something fast enough? This is where some new technology would have to come into play. There have been searches for 119 and 120. They have not been successful yet, but it's pointing us in the direction of where people would need to go to do that. It might be a few more years or many more years, it's hard to say, but I think at some point we will see some more elements on the periodic table. It'll be a question of what is the technology advance that needs to happen for us to push beyond that.
In the meantime, these awesome elemental creations are helping us push the boundaries of our understanding of everything from quantum physics on the inside the atom scale to the conditions inside supernovas. And I, for one, can't wait to see what we smash together next. If you liked this video, make sure to subscribe to our channel for more Inside the Lab videos coming soon, and don't forget to watch our periodic table primer here. Follow us on social media for more exciting elements content, and as always, thanks for watching. See you next time.